Hello Berlin, Buzzwords. It's great to be here. My name is Jordan Mendelson. I work for a small open data nonprofit named Common Crawl, whose goal it is to provide an archive of the web for anyone to download, play with, run analytics on, or whatever you want to do. And today, I'm going to be talking about big data for cheapskates. So, what is a cheapskate? The dictionary definition is a person who is stingy and miserly. I admit, when I named this presentation, I did not recognize this. This is kind of a negative thing. I actually always thought of somebody as a cheapskate as someone who made cool stuff with very little money. Someone who would rather build something than buy it. And imagine from this group, there's quite a few other people here who have possibly built things rather than buy it. Show of hands, who here has spent some time building something rather than buy something off the shelf? Good, good. Welcome, cheapskates of all kinds. I feel not so lonely today. So, about me, I have always been a cheapskate, mostly out of necessity. My first company I formed in 1995. It was a very small internet service provider that served the East Coast of the United States. It was very poor, very poor. It ran out of a closet in the back room of a movie rental store. The whole thing was a converted desktop machine that ran Slackware Linux, hooked up to a bank of modems that we went out to the local electronics store and purchased. And everything ran open source software. And this was at a time when not everything was entirely stable. I believe we were running like Linux 1.2.5 at that point. All of our web server, Apache was new. We ran NNTP servers, crazy things like faxed email gateways. But we built some cool stuff, and by diverting that money that we would have spent buying, giant Sun Spark machines and SunOS, we were able to buy a second internet connection and upgrade the speed. And pretty soon, we had a pretty good business. My cheapskatedness followed me, if that's a word, to Napster, where we were a group of 5 guys. We did not have much money, but we had users. Not a lot of users then, but we had users, and they were growing very, very rapidly. So we did what we knew how to do. We bought and made some cheap Linux servers. We ran experimental copies of the Linux kernel that were constantly being patched and hacked up, thankfully, partially by Alan Cox, who every single time I'd send him a kernel oops, would send me a new driver for my Ethernet cards, which were just constantly going out. And we were spending a lot of our time just trying to get, an extra 1,000 users on every machine, and then an extra 10,000 users, an extra 40,000 users. And even when we had money, and we did in the end up with a fair bit of money, it all went to legal bills. None went to hardware. Certainly not any that I noticed personally. So it wasn't until I joined LinkedIn in the data analytics group that I had the luxury of an idle cluster of machines. And I don't know if you can understand how this feels, but I had begged, pleaded, and borrowed every ounce of CPU power I could find. I was using desktop machines inside the office to run jobs because I had nothing else, nowhere else to go. We built a screensaver literally to go, and while people were home, go in and crank out a little extra power. But by the time I got to LinkedIn, I realized something. My cheapskatedness, it was too far ingrained. I was hopeless. I didn't know what to do with all this extra machinery. Luckily, in the area of big data that we're in, the kinds of skills that cheapskates like me use on a regular basis are now back into demand. So what we're going to talk about a little bit with this talk, the overarching message here is that anybody here, anybody at all, can do big data analytics on a very, very limited budget. So we're going to talk a little bit about getting data. We're going to talk about tools. We're going to talk about planning, which is extremely important when you're talking about big data on a budget. We're going to talk about some techniques, and then we'll have some time towards the end for questions and answers. So, getting free data. I admit that a few years ago, I thought that big data was something that only big organizations, enterprise organizations did. When you're Facebook, or you're Google, or you're Yahoo, and you have tens of thousands of machines just sitting around, they're purchasing the newest, greatest things all together. But not only are they giving you the hardware, but your systems are generating terabytes and terabytes of data on a regular basis. You don't have to go looking for data. So I thought, even if I had the compute power, what was I going to use it for? But in the era of open data that we have today, there's been tremendous growth in the variety and the size of data that you can download and use publicly for free. The open data movement has really grown by leaps and bounds. My own company, Common Crawl, provides for free a 250 terabyte archive of the web from crawls from the last 5 years. That you can go and do whatever kind of weird analytics, stuff that you would only be able to do if you were somebody inside of a search engine like Google. You as an individual can do. But there's other organizations. There's the 1,000 Genome Project. 1,000 Genome Project has put up a 200 terabyte archive of genomic sequences for over 2,000 individuals that you can go on directly through their website or through Amazon's public data sets and just use, if you know something about genetics, which I don't. But it goes beyond that. The US government and the UK governments, plus cities and states like Berlin, have opened up data portals that include everything you can think of. If you want crime statistics on a block-by-block basis, they have it for you. If you want air pollution measurements, it's there. You want water pollution measurements, it's there. The Berkeley Earth Project has aggregated hundreds of data sources out there. If you're interested in climate change, they have 1.6 billion reports on temperature measurements made since the 1800s from tens of thousands of weather stations around the world. If you're interested in image processing, you can go to ImageNet, and they will hand you an archive of 14 million images to do whatever you want with. And I could go on and on and on. But the bottom line is, we live in an era of abundance. And through this, you can do some really, really cool stuff without paying any money to get the data itself. So I was going to plaster the slide with URLs and logos and you know, free data, open data movement's a little fractured. There, as I said, governments have portals, cities have portals, individual projects have portals. There's only a couple catalogs out there, and they're not very complete. But this one Quora link actually provides a better starting point than anything I could put up on the slide. And don't worry about writing it down. This deck will be online after the talk. But it really does a really great job. So let's talk a little bit about tools. I'm sure many of you are aware there are some really great analytic tools out there, both free and commercial. Unfortunately, a lot of the really good ones, you know, SciPy and the like, are really built for an R and things like that, are really built for smaller data sets. When you start talking about processing terabytes of data, they kind of fall down. And the commercial ones, and if you're a cheapskate, the commercial ones are just, they're probably outside of your reach, you know? As much as I love Splunk as a tool. I've used Splunk at a previous company. Right now, as an individual, I don't have a couple $1,000s to plop down on a log processing tool, as great as it is. So what can you do as an individual? I personally believe that Hadoop is the best tool out there for big data batch processing. I mean, it's free, which is always great. There's a lot of support tools that exist out there, a lot of layers you can put on top of it. But the fact of the matter is that Hadoop is not easy. This is not even as easy as a database server, which has a pretty high bar of usage for somebody who's non-technical. I have a friend of mine who runs a analytic consulting company who mostly deals with giant enterprise organizations. And he told me this story about a Fortune 500 CEO, that would be funny, CEO, Fortune 500 CEO who, you know, had been following big data. He had gone to, I think he went to Strata or something, sold by all the slick people there, bought a gigantic Hadoop cluster, beautiful systems, you know, everything you could ask for, fast networking, all the RAM you could ever use, SSD drives all over the place, you know, more CPUs than I've ever seen in my life, to analyze all the data that was coming out of his brick and mortar stores. And he calls up my friend a couple months later, and says, hey, you know, nobody ever told me that it would take 50 engineers for me to generate a report. He came from a world where somebody went in, they opened up Excel, you know, they took their high-end numbers and then they plotted some stuff. That was how they generate reports. But now, no matter, you know, even with this fancy, schmancy machine and installation, it still took a lot of people to do some of the things that they wanted to do. And these problems are magnified when you're talking about running Hadoop in a limited resource environment. If you don't have, you know, 200 gigabyte machines with, you know, 32 cores and lots of SSD drives and 10 gig switches and everything, it's harder. But the thing is Hadoop works. It really does. Over the past couple of months, I have processed petabytes of data through Hadoop. It has reasonable reliability, and it's reasonable. It is pretty resilient to errors. If your nodes go down, it will try its best to come back up again. It, generally speaking, doesn't lose data. And it really, really shines when talking about processing a lot of messy data. I mean, if you're talking about open data, which is often pretty messy, I find that Hadoop works better than anything else I've used in the past. And thanks to the contributors from the Apache project and outside the Apache project, it's just getting better every day. And I expect in a few years, a lot of the problems that exist today will be a bad memory. So let's talk a little bit about this. You have your data, and you are a cheapskate. You don't have, 100 machines, large machines to run your data on. And if you did, somebody else is probably using them. So what do? Well, for most of us, that means choosing a cloud service. Now, up here, I've just listed a couple of the major clouds. Next to them, I have some prices. The prices are mostly there to help you understand the range of types of machines that exist for each of these clouds. But the fact of the matter is price per machine per hour is not the only thing you look at when you're choosing your cloud. Each cloud service has its ups and downs. Some have much, much, much faster networking. In some cases, there's at least one service who, for Hadoop, will cluster their machines for your Hadoop cluster all on the same switch right next to their blob or S3 type storage system to make it much, much, much faster. In the case of Google's one of the unusual ones. Google will, after 10 minutes, start charging by the minute, whereas everybody else rounds to the nearest hour. And some take seconds to bring up an instance. Some take tens of minutes to bring up an instance. So in any case, though, they all charge for outgoing bandwidth. And they rarely, I don't think any of them, charge for incoming bandwidth. So what that means is you need to choose your cloud very carefully, because once you set the data there, it's going to cost you money to get it back out again. So I'm just going to bring up a couple tips on deploying Hadoop inside of these kinds of clouds. This is a big one. If you are using Amazon, and I cannot stress this enough, use Spot instances. I mean, I seriously came up here thinking that I could say this one slide, drop the microphone, and walk off stage. It's that important. Through Spot instances, you will look to save about 90% off of what your on-demand instances cost, which is pretty major with no real work. If you are willing to work weekends, which I'm sure not many of us are, if you're willing to work weekends, or at least start your jobs on weekends, the spot pricing will rarely fluctuate past 15% of the on-demand price. And due to inefficiencies in how Amazon's bidding system works, you can often get some very, very, very big instances from them with zero contention. Nobody else wants them. Everybody wants like the mid-level M1 extra large instances. And if you look at the charts of price histories for their giant cluster compute instances, the price is completely flat. So use Spot instances. It'll make a huge difference. Now, once you are using Spot instances, if you're on Amazon, roll your own Hadoop. And I say this because the way Amazon has a service called Elastic MapReduce. It's beautiful in terms of ease of use. It does everything you'd want to do. It brings up Spot instances if you want. It brings up on-demand instances if you want. The thing is it's priced. You will usually pay more money for EMR than you will for your Spot instances. because they're priced as a percentage of the on-demand price. To give you a better idea of this, this is some pricing. And then this is for the biggest cluster compute system that Amazon provides. And with spot instances, with your own Hadoop, you're paying about €2 an hour for 160 CPUs, 600 gigs of RAM, and 33 terabytes of local instance storage. If you were to go and get the exact same thing with on-demand instances, you load it up with EMR, you're paying 25.8 euros an hour, which is obviously a big savings. The same thing is true with the smaller instances. This is the M1.extra large, 40 of them. For that, you've actually end up with more disk, which is kind of funny. The previous instance, you get 10 gig E. This one, you'll get about gig E. So there's some slight differences there. You'll pay, €1.59 an hour for these instances. And you can do a lot with that. That's a pretty big cluster. So the last thing I want to talk about in terms of deploying Hadoop in the cloud is deploy your Hadoop instances only as necessary. Now, this might be really obvious to people here. You're all a bunch of smart people. But I've had a lot of conversations with people who treat cloud computing as they would servers they purchased and put in their data center. What I mean by that is they start up their servers, they get some reserved instances, they start up their servers, they configure their Hadoop cluster, and then they just let it run. Doesn't matter if it's used, doesn't matter if the type of instance they chose is wrong, they just let it run until something breaks and somebody goes in and fixes it. The thing is you can spin up 400 Hadoop instances on Amazon in less than 6 minutes. Master, slave, the whole kit and caboodle. So if you treat your Hadoop deployments as transient, you reap a lot of benefits. And some of them I'm going to talk a little bit about later, but they mostly relate to, the cost that you're not paying while they're not running and the flexibility to choose the type of instance you want for the job you're going to run. So, no talk about Hadoop can be complete without planning. Planning is when you don't have a lot of money, is something that's paramount, honestly. It requires a lot more restraint working with big data than it does with hacking up a web app, for instance. I personally am somebody who's a little quick and dirty. I like to experiment on production machines. I am one of those people. I like to throw something up, see if it works, re-optimize it, throw it up, see if it works. This does not work in the world of big data, where every single time you run something, it costs you real money. So I like to ask myself a couple questions. What am I going to do with this data? Frankly, when I think of this question, I list out every single job I ever expect to do with this data. Just long list of things so that I can do these next couple steps. And then, how often is this data updated? If you're talking about third-party data, it can be updated in a bunch of different ways. They can give you just your new data. If you're talking about things like the Department of Labor Statistics, they revise their old data. So if you processed it before, you have to reprocess it again. So it's very important to pay attention, how your data is updated. Finally, how often does this job need to be run? Are you in a financial services company where you're doing day by day, moving averages, or is it just something you just run one off? And so what I like to do is I like to build charts. And your chart might not look anything like this. This is mostly fit for this slide. But I list all my jobs, statistically impossible phrases, which is fun to do. Page rank, which is not so fun to do. I list out, the frequencies, and finally I list the intermediate data that I need between them all. And I list the intermediate data because a lot of my jobs tend to use the same kinds of data, and I will treat usually intermediate data as something to throw away. It's in my pipeline. It's something that exists, and then once it goes into the next pipe, I just toss the data. But if you are running jobs frequently, or a lot of jobs use the exact same intermediate data, you might choose to keep it around, and which will save you a lot of time and energy in creating the exact same intermediate data with various types of code. So let's talk a little bit about techniques. Many techniques I'm going to describe are the opposite of what some people might suggest, especially those with large clusters of machines. And there's a very good reason for this. My techniques are not optimized for speed. They are optimized for cost. And you might think that speed and cost are directly related. But in a cloud environment, nothing could be further from the truth. The way clouds price instances means that you can run a lot longer on an instance with very, very little memory and get charged almost nothing, and run the exact same amount of time on a bigger instance with more memory and get charged a lot more. So very important. And finally, though, I just want to say that when you're doing these kinds of optimizations, always be cognizant of what you're doing, basically. I have found myself in the position of optimizing for the last 1% to get that last 1% of my performance because, I knew how to do it. It would just run that much faster and I could save that much more money. And then 3 days later, went out, okay, I was very happy with myself. And then I worked out how much I saved. And it was less than the cost of the coffee that I used to build the optimizations themselves. Optimization is an exercise in diminishing returns. So always optimize, to get your big stuff done first. And if you're really bored, work towards the small stuff. So before going into specific techniques, I thought this was very important to put up. Your ultimate goal with big data is to turn it as quickly as possible into small data. Your goal is not to generate more big data. Your goal is not to have big data around. Big data is difficult to process. The types of algorithms you can use on big data are limited. And frankly, it's impossible to digest in and of itself. So you should not be afraid of shrinking big data to something more usable. Small data, on the other hand, is extremely flexible, and if you can get small data small enough, you don't even need a Hadoop cluster to process it. Load it up in R and be happy. Spit out all the charts and graphs and everything analysis that you want to do once you turn your giant data into something smaller. Now, personally, I like to shrink it to something like this. And this first line represents my input. It's like job 0. And I like to shrink my data by about 80% or more on my first pass. And you can shrink it in a bunch of different ways. You get filtering, segmenting, summarization. You can even use compression, tossing data and just using random samples. I mean, there's lots of ways of going about it. But a lot of the techniques I'm going to talk about are essentially based on this idea, getting the data small quickly. So let's talk about the first technique. Remember I said to spin up your job instances as necessary, and especially for the job type you're going to run. Well, the reason for that is that cloud providers, the pricing they use for instances is vastly different between instances that are optimized specifically for memory, or specifically for CPU, or specifically for networking, or specifically for storage, than they are for general purpose machines. Okay? So what that means is that you can take the steps of your job. Okay, so you have some specific job, split it up into CPU-heavy pieces, memory-heavy pieces, network-heavy pieces, I/O-heavy pieces, and then split them into individual jobs and run each individual job on completely different instance types that are sized just right for the job you're going to run. Also, what you can do is take the exact same job and segment your data itself to run on different segments, different instances for that segment of data. Say you have a piece of data that it takes a long time to process 10% of it, or requires a lot of memory or a lot of CPU, and the other 80% requires very little time because they're really small records or everything's ones or something simple. Let me just give you an example to help clarify that. As I said, I work for a nonprofit. We build and maintain an open archive of the web, and we deal with a large amount of data. I said we have 250 terabytes of data. Well, in the processing stages of building that 250 terabytes, we exceed several petabytes of data, during all of our stages. So I just put up here a couple of the jobs we run. One is web crawling. Obviously, we have to get this data somehow. Web crawling takes weeks, to run. Uses very little I/O, uses very little RAM, uses a little CPU, and uses a little networking. The reason why it doesn't use a lot of networking is because our crawlers usually, they're very, very polite. And in order to not flood web servers with requests, we back off pretty heavily. So on the flip side, parsing, which is what we do so that we can prepare extracts of data, like raw text that goes along with this web page, minus all HTML tables, or for PDFs or whatnot, and do language identification, run various hashing algorithms and whatnot. Uses a lot of CPU, and it uses a lot of memory, and it uses still a moderate amount of I/O and a moderate amount of networking. So we could have easily combined these two jobs together, two tasks together. After all, when you are downloading a web page, the web page is already in memory. If we went and did a parse step right there, that means there's no disk I/O that we'd have to do. There's no networking I/O we'd have to do. We just plop it in, run it, parse it, and be done. The problem with this is the crawl takes weeks, whereas the parse step takes days. And in order to do this kind of thing, we would have had to run much bigger machines for weeks in order to do our crawl to handle the excess memory that parsing uses. Whereas if we split them up, we can use very, very small machines. And for instance, on Amazon, we might run like M1 lot larges, which we pay 2.6 cents per hour per machine to run, meaning we could do a crawl of a couple billion pages for a couple $100. And then run our parsing step on much bigger machines for a couple days. We can also go past this and split our parsing job up into two pieces. So it turns out parsing is really, really expensive if you're parsing really big documents. But most of the documents in Common Crawl are really small. So if you're parsing things that are over about 200 kilobytes, it uses sometimes in the order of 10 times more memory than you're parsing things that are under 200 kilobytes. So what we can do is segment our data, run our small parses on, again, small machines, and then run our big parses, which are 10 to 15% of our data on big machines, and save ourselves overall 30 to 50% in costs with very little engineering effort. And this is, widely accessible to, I'm sure, many of the things people are doing. But let's just go into another interesting thing. We talked a little earlier about keeping some intermediate data. This is a difficult one. As I mentioned earlier, storage services charge for storage. Cloud services charge for storage. And you have to think to yourself, well, is it worth it for me to keep some of this intermediate data around? There are a bunch of different factors involved. You have to keep into account the constant lowering of prices for cloud services, which happens literally every 6 to 9 months. In the case if you're in Europe, you have to worry about the euro fluctuation. You have to worry about the time it takes to generate the data versus the time it takes, the cost it takes to store the data. But, we all generate the same kind of intermediate data. And sometimes they speed up our processing quite a bit. And that's something you really have to take into account when thinking about whether you're going to keep it around. And if you do keep it around, sometimes it's worth it to throw away the original data. So, spend some time looking at your intermediate data, deciding whether or not it's worth it to keep it around. And if it is, great, and you'll probably save yourself a lot of time and money down the road. The final technique I'm going to talk about is paring down your data, which I did mention earlier, which you do, by sampling, segmenting, filtering, and summarizing. Excuse me. Sometimes, though, the algorithms you use to filter down your data are actually quite expensive. Certain classifiers are pretty expensive. Some clustering algorithms are pretty expensive, and especially when you're talking about running it on 6, 10, 12, 50 billion records. So I like to use an algorithm, a technique of running really, really fast but dumb algorithms first, followed by really slow but smart algorithms second. And I could debate up here, the benefits of various classifier algorithms, or whether using a bbit min hash is better than a sim hash. But the fact of the matter is that sometimes you can get by with using something that you would never, ever use on a real set of data to just shrink your data set down to just the stuff that's likely to be caught by your second filter. So let me just give you an example from Common Crawl. So we do deduplication of data. So every single time we run a crawl, we deduplicate things so we don't have 3 million copies of some coming soon web page, which nobody wants to see. For 2013, for May of 2013, we have 40 terabytes of web pages, about 2 billion. And we're just starting this. This was all fetched using Apache Nutch, so that we've been experimenting with. There's a bunch of algorithms you can use for deduplication of near neighbors, close duplicates, sketching, SimHash, locality-sensitive hashing, variants like that. They have their pluses and benefits. Generally speaking, in order to get these things to go fast, you have to trade off something. Usually it's memory. In other cases, you end up with what's the word I'm looking for? Data explosions, excuse me. So, for instance, a SimHash, in order to do a SimHash really efficiently, there's a bunch of ways. One of the ways is to shingle the heck out of it. And so you end up with like 20 semi-small fingerprints where you had one before. And then, so if you were talking about doing it on 2 billion documents where you would have 2 billion SimHashes, then you have 20 times that. And we like to do our deduplication against not just our new data, but then against our existing data as well. So it just blows up and blows up. So instead, what we do is the world's dumbest algorithm that works, has huge false positive rates. I mean, truly, truly terrible false positive rates. But it is really, really, really fast. So what we do is we take the top N words for a document, we alphabetize them, and then we hash them. That's it. It's fast, it's easy, it can be used on the slowest machines Amazon provides outside of their micro instances. And I'm working on getting them to work on micro instances so I don't have to pay for it at all. Then what that does is that it shrinks our 2 billion hashes down to about 800 million. But it goes beyond that. It shrinks each bucket, each key, down to at maximum about 100,000, on average about 6,000 to 8,000. So all of a sudden, doing a SimHash is totally doable and extremely fast. And what that kind of looks like is this. We have ourselves a giant input, it's, what did I write here? It's about 40 terabytes of data that we turn into 2 billion SimHashes. We actually do the SimHash calculation and the really dumb hash calculation at the same time because it might as well. It's just there. And at the very end, very, very, very end, last bucket, we end up with 300 million URLs that are duplicates that we can then pull out of our index. And we do all this for, a couple $100, and this is lightweight stuff. Actually, I forgot, we have one last set of techniques. This is very important for those of us who are dealing with bad external data. Our data can be corrupted, data that's giant and probably has corruptions in it. And that is to avoid errors, avoiding specifically catastrophic errors. Look, the chances of your code breaking increases proportionally with the size of the data you're processing. This seems to be an inevitable fact. And this usually happens when processing the last record of a 10-hour job. I don't know why. It just happens. Like or when you walk away, or you start on a weekend. It happened. If you start on a weekend, it was the first record, and you just didn't notice it. So there's some obvious ways of mitigating this problem. I like to process the last record first. I'm just kidding. Although I've considered it seriously in the past. Though I cannot stress how important it is, though, to always test your jobs on sample data first. And as somebody who is kind of fast and dirty and loose and doesn't like to test things very frequently. I have been beaten into submission into doing this after losing many, 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 many days to jobs that fail for all sorts of reasons. And I'm talking about things like miscompressed files that somehow blow up the decompressor. HTML pages that cause my parsers to get into infinite loops. I'm talking about honestly, I believe stray solar particles hitting my memory on my machine at the wrong time. That's what I'm convinced of because I haven't been able to trace it down. It seems the most likely. The next thing you can do, though, and this is a little more regular, is skip over bad records and skip over slow records. There are going to be edge conditions that you can't predict, okay? So to minimize your chance of a bad record taking down your long job, just skip over it. Log it, skip over it, be done with it. And if you're using a third-party library, to process your data, I highly recommend setting a time limit for the time that record's allowed to be processed. And if it hits, just canceling it, just continuing on your way. And there's a lot of ways of doing this. You can use Hadoop's built-in stuff. This is all written in Python. It's not accurate. It's my pseudocode. So, but you can use Hadoop's built-in way of doing it. It's really not efficient. The way Hadoop works is essentially if your mapper or reducer crashes, it will go in, and if you flip these flags on, it will then skip the record you were processing so that next time you will continue on your way. But what this does mean is that it goes and reprocesses all the other records that you'd already processed. The alternate way is to use something like threads or processes to stick a proxy in between your actual data processing process and your Hadoop process, and then just kill it, if it's going wrong. Undo the changes, log the whole thing, and be done. Of course, you can do a lot more elegant things than what I've done here, but frankly, they're not that hard to do. They just require time and effort to set up your templates. So, in summation, I'm going to just talk about what we've talked about today. Plan your jobs, really very, very important stuff. Filter your data as quickly as possible, either through literally filtering or through sampling or through summation or cleaning or compression, whatever you need to do to shrink it as quickly as possible. If you're using Amazon instances, use Spot, roll your own Hadoop. Start Hadoop as necessary and be flexible with the instance types that you run with your jobs. Keep some intermediate data, depending on whether or not it benefits you or not, and be cognizant about the type of intermediate data you keep around. Use algorithms wisely. Again, sometimes the best algorithms are not going to be the cheapest, so be cognizant of how your particular deployment affects your algorithms. And, of course, avoid errors when possible. And finally, just to wrap this whole thing up, I would like to say that anybody can do big data. And I fully expect that you guys can all go home, log on to the core link, start up your Hadoop instances. We have some great tutorials at commoncrawl.org on, MapReduce in like 5 seconds for less than less than €1. You could do whatever you want, and really, really do some of the stuff that only larger organizations are doing today. Thank you.